So I kind of jumped ahead on the end of the last section, so I'll kind of review it again now. Where we're moving on to section 7. So our body is going to use the nutrient pools, which basically our nutrient pool is how much amino acid, how many carbohydrates and fats do we have in our body. Moving on. Okay, so the catabolic and anabolic steady state, when we're talking about some of the nutrient pools, we can kind of classify them based off of which macromolecule we're talking about. And when we're talking about the amino acid pool, that's our body's total supply of free and available amino acids. So we lose small amounts of amino acids and proteins every day in our urine, and also in any skin cells that we have sloughing off, as well as our hair. So we have to replace these lost molecules via our diet. If we don't, amino acids are rising. We're going to get amino acids by breaking down tissues in order to get enough amino acids back into our pool. So pool is the source for helping to resynthesize our body proteins, for forming amino acid derivatives, and as well as gluconeogenesis if we need to make glucose from something that wasn't a carbohydrate derivative to begin with. Not all events of the amino acid metabolism occur in all cells. So for example, only the liver can form urea. But either way, we have a common connection based off of our common amino acid pool. When we're talking about carbohydrates, carbohydrates are easily converted to fats. And so we kind of consider our carbohydrate and fat pools collectively or together. So there are two major differences between the carbohydrate fat pool and the amino acid fat pool. So the fats and carbohydrates are going to be oxidized directly to produce cellular energy in the form of ATP. Whereas when we're talking about amino acids, those can be used to supply energy only after being converted to a keto acid, which is a citric acid cycle intermediate. So remember, it went right into the citric acid cycle. If we're talking about glucose or fats, those can become intermediates of glycolysis. If we have too many carbohydrates or fats, we can store them. Or we talked about before, we cannot store proteins if we have excess amino acids in our pool. So we would actually oxidize those for energy or convert them into fat or glycogen. So I like this image because when we think about cellular respiration and glycolysis, we typically think of only being able to utilize glucose. But this image gives you a nice flow chart of how we can actually use all of our macromolecules, and they can go in and enter in at various places within cellular respiration. You're not responsible for knowing all the specifics. Again, what we talked about previously when we talked about these macromolecules being metabolized. So we have the absorptive state or the fed state, and this is going to last for a couple hours after we begin eating, where we actually have nutrients going into the blood and being absorbed from our digestive tract. During this phase, anabolism or building up is going to exceed catabolism and breaking down, and we're going to begin storing nutrients. Glucose is going to be our major source of energy, fuel for energy, and our amino acids and fats are going to be used to remake any worn out body proteins that we might have. If we have any excess metabolites, these are going to be transformed to fat if we don't need to use them in any sort of anabolic process. So let's talk about carbohydrates. So carbohydrates, we know, are a major cellular energy fuel. They can be converted in the liver to glycogen if we have excess glucose, and they can be stored in the liver, or they can be converted into fat. So most fat packaged with proteins form what we call VLDLs, or very low density lipoproteins. And these are going to be released to the blood for storage in adipose tissue. We have blood-brain glucose that can enter into cells, and then excess glucose stored as glycogen. And we can store our glycogen either in our muscles or as fat in adipose tissue. When we're talking about triglycerides, most of the fat digestion that we talked about enters into the lymph as chylomicrons, and then our triglycerides are hydrolyzed into fatty acids and glycerol, which then can enter into various stages of cellular respiration. We do have an enzyme called lipoprotein lipase that is going to catalyze the fat hydrolysis. It's really, really active if we're talking about muscle and fat tissue, which likes to use lipids as a source of fuel. However, most glycerol and fatty acids are going to be converted back into triglycerides for storage. Amino acids, so absorbed amino acids are going to be delivered to the liver. That's where we have our deamination that's going to occur, where we get our keto acids. Our keto acids can then enter into the citric acid cycle in order to make ATP or energy. Alternatively, they can be converted in the liver into fat. Most of the amino acids are taken up by cells and are going to be used by protein synthesis. So here's our basic theme of anabolism and energy storage during the absorptive state. So our amino acids are going to be used to make proteins. We're also going to have glucose that's going to be polymerized into glycogen, and our glycerol and fatty acids are going to form triglycerides for storage. So during the absorptive state, again, a couple hours after we begin eating, are going to be mostly anabolic processes where we're building molecules from their monomers. The major energy fuel during this state is going to be glucose that we're bringing in from the diet. And if we're talking about liver metabolism, we're going to have amino acid deamination and use for energy or stored as fat. This is a nice flow chart kind of giving you what's going on depending on what organ we're talking about. If we're talking about muscle, our liver, all tissues of our body, as well as storage of triglycerides in adipose tissue. Okay, when we're talking about hormonal control of the absorptive state, insulin is really going to kind of direct all of the events of our absorptive state. So right after we eat a meal or begin eating, our blood glucose levels and our amino acid levels are going to increase. And the increase in our glucose and amino acids are going to stimulate those beta cells of our pancreatic islets to secrete more insulin. We also have a GI tract hormone called glucose-dependent insulinotropic peptide, or GIP, and we have parasympathetic stimulation to also help promote the release of insulin. But the goal is to have insulin release, because insulin is going to go in, bind to receptors, and facilitate diffusion of glucose into our muscle cells and our adipose cells. The one exception is going to be our brain and our liver, which take up glucose even if we don't have any insulin being released. So insulin is also referred to as a hypoglycemic hormone. So it's going to take glucose out of the blood and put it into tissues, ultimately lowering blood glucose levels. It's also going to help enhance glucose oxidation and storage while inhibiting other processes that might increase blood glucose levels. Again, a nice flow chart kind of outlining everything that we've talked about. And we can move on to the post-absorptive state. So the post-absorptive state is also referred to as the fasting state. And this is the period when our gastrointestinal tract is completely empty and body reserves are broken down in order to supply energy. So we have net synthesis of fat, glycogen, and protein ends that we had in the absorptive state, and we start actually breaking these substances down. So primarily we're going through catabolic reactions. And the goal of the post-absorptive state, again, is to help maintain our blood glucose levels between meals. So we're making sure that we have glucose readily available in our blood, because a constant blood glucose level is important because our brain only uses glucose as an energy source. So we have to have glucose available. Also during this time, it's going to promote the use of fats for energy. And like I mentioned, because our brain can only use glucose as a source of energy, we have what's called glucose sparing. So our body uses more non-carbohydrate fats and protein as sources in order to conserve glucose for our brain. So where does the blood glucose come from in the post-absorptive state? Sources include the glycogen that we had stored in our liver and skeletal muscle cells. We can also convert amino acids into glucose and break down our tissue proteins. And we can also get our fat breakdown. So step one for blood glucose levels is glyconeolysis. Genolysis that's occurring in our liver. So the liver glycogen stores are going to be the first glucose reserves that are going to be used. Then we have glyconeolysis in skeletal muscles. So our glycogen that's being stored in our glycosomes in our skeletal muscle is going to be utilized next. Then we're going to start breaking down our fats. So we have lipolysis in adipose tissues as well as our liver, and the glycerol used for gluconeogenesis in our liver. And last source of blood glucose is going to be from the breakdown of our cellular proteins. At this point, our proteins are going to be a major source of blood glucose if we are fasting for long periods or when we've depleted all of our glycogen and fat stores. And that's where we're going to have our amino acids go through deamination and ultimately be converted to glucose in the liver. So here's a chart kind of giving you the breakdown of what's going on during the post-absorptive state, mostly catabolic reactions where we're taking our macromolecules and breaking them down into our monomers that we can use as fuel to make ATP. This is to help keep our blood glucose levels consistent while we don't have any food intake or nutrient intake. At this point, we have glucose and fatty acids being our primary source of energy. And in our liver, we have amino acids being converted to glucose if necessary via gluconeogenesis to make more glucose. And again, a nice illustration showing you the pathways and what's going on and occurring in our muscle, our liver, our adipose tissue, and along with our brain, which can only utilize glucose. So hormonal control in the post-absorptive state, we do have several hormones along with the sympathetic nervous system that help control these events. So the post-absorptive state is going to be triggered by a reduction in insulin release as our blood glucose levels drop. So we have glucagon. And if we have low blood glucose levels, this is going to stimulate the alpha cells of our pancreatic islet to release insulin antagonists, which is called glucagon. And like other hormones during the post-absorptive state, glucagon is a hyperglycemic hormone, meaning that it's going to help raise blood glucose levels. And glucagon is going to basically target our liver and adipose tissue. And what is it going to do there? It's going to cause our hepatocytes to respond by accelerating glycogenolysis, so breakdown so we can get more glucose, and gluconeogenesis, making glucose from non-carbohydrate products. It's also going to help adipose cells mobilize their fatty stores, so go through lipolysis, and then release those fatty acids and glycerol into the bloodstream. So here's a nice flow chart, again, kind of showing you what's going on during the post-absorptive state. I kind of recommend you go through and make sure you understand this. So the sympathetic nervous system plays a huge role in helping supply fuel quickly in the event that our blood glucose levels drop suddenly. So our adipose tissue is innervated by the sympathetic nervous system, and we can quickly supply glucose if we get low blood glucose levels. Other hormones also play a role. Metabolism and nutrient flow are also influenced by hormones other than glucagon and insulin. We have the growth hormone, thyroxine, sex hormones, corticosteroids can also have effect on metabolism, but most of these are going to have